Tonight, we begin with a star that is already dead. This will be a slow, quiet astronomy journey, built to remain clear, even if your attention begins to soften. Not dead in the dramatic sense of an explosion, but in the quieter astronomical sense that its nuclear fuel is gone. What remains is a white dwarf, a compact stellar remnant, roughly the size of Earth, carrying a substantial fraction of a star's mass inside that small volume. Some white dwarfs have been cooling for billions of years, and they are still warm. That simple fact leads us toward one of the strangest ideas in the long future of astronomy. If a white dwarf is no longer producing energy through fusion, then the heat it contains cannot last forever. Little by little, it radiates that stored energy into space. Its surface grows cooler. Its light becomes weaker. Given enough time, the remnant should eventually become so cold and faint that astronomers give the hypothetical final state another name: a black dwarf. No black dwarf has ever been observed. More importantly, according to our present understanding of stellar evolution, none should exist yet. The universe is about 13.8 billion years old. That sounds ancient on every human scale. It is older than Earth by billions of years, older than the Sun, older than the Milky Way in its present form. But for the cooling of a white dwarf, 13.8 billion years is not an immense amount of time. It is only the beginning. This creates a gentle contradiction at the center of our story. Physics allows us to describe an object that the universe itself has never had enough time to produce. We can study white dwarfs that exist now. We can measure their temperatures. We can watch how populations of them change with age. We can test the physics that governs their interiors, and we can even see evidence that some of their cores are beginning to crystallize as they cool. But the final state lies far beyond anything the present cosmos can show us directly. So our journey tonight will begin with what is visible. We will start with a white dwarf that still gives off light. Then we will move inward into the quantum physics that keeps it from collapsing. From there, we will follow the heat as it slowly escapes through crystallization, changing heat capacity, and the cooling patterns astronomers can measure in real stellar populations. Only after that will we travel forward, far beyond the current age of stars, far enough to ask when a white dwarf might finally become something no telescope has ever seen. You do not need to keep every number in mind. The important thing is simply to follow one fading star and to notice how much future can be hidden inside a very small point of light. That small point of light is easy to underestimate. A typical white dwarf is roughly comparable in size to Earth, yet it can contain more than half the mass of the Sun. Matter inside it has been compressed to densities far beyond anything we encounter naturally on our planet. But the remarkable part is not simply how dense it is. It is that the star can remain that dense without continuing to collapse. In an ordinary star such as the Sun, gravity is always pulling inward. The star avoids collapse because its hot interior supplies pressure. Nuclear fusion releases energy. That energy keeps the gas hot, and the hot gas pushes outward against gravity. A white dwarf has lost that arrangement. Fusion has ended. The reason comes from quantum mechanics. Inside a white dwarf, atoms have been squeezed so tightly that their electrons no longer behave as they do inside ordinary matter. Instead of remaining attached to individual atomic nuclei in familiar electron clouds, many of those electrons move through an extraordinarily dense interior. At these densities, a rule called the Pauli exclusion principle becomes crucial. Electrons belong to a class of particles that cannot all be placed into the same quantum state. As gravity tries to squeeze the matter into a smaller and smaller volume, the available low-energy states fill up. Further compression forces electrons into progressively higher momentum states. That creates pressure. Astronomers call it electron degeneracy pressure. It does not require nuclear fusion. And it does not disappear simply because the white dwarf cools. A white dwarf behaves differently. Its principal structural support comes from the quantum arrangement of its electrons. Cooling changes its thermal energy, but it does not switch off the exclusion principle. So the star can become much colder while remaining almost the same size. This distinction will matter for everything that follows. The fading light tells us how much heat the white dwarf still carries. It does not tell us whether the star is about to collapse. For most isolated white dwarfs, cooling and structural survival are almost separate questions. There is, however, a limit to what electron degeneracy pressure can support. As the mass of a white dwarf increases, gravity becomes stronger. The electrons must occupy increasingly energetic states to resist the compression. Eventually, the physics reaches a boundary. That boundary is associated with the Chandrasekhar limit, named for Subramanian Chandrasekhar, who worked out underlying result while still a very young physicist in the early 1930s. For an ordinary white dwarf, the maximum supported mass is roughly 1.4 times the mass of the Sun, with the exact value depending on composition and other physical details. Below that scale, electron degeneracy can support a stable white dwarf. Near or beyond it, the situation changes. In interacting stellar systems, additional mass can drive processes that lead to collapse or thermonuclear disruption, depending on how the mass is added and what happens inside the star. Those are different endings from the one we are following. Our white dwarf remains comfortably below that boundary. It does not need to explode. It does not need to shrink into a neutron star. It can simply remain where it is, compact and stable, while its temperature falls. And that gives this object an unusual future. Gravity has already compressed it, nearly as far as electron degeneracy will allow. Fusion has already stopped. Its structure no longer depends on staying hot, so almost all that remains to change is its thermal state. A normal star shines because it is continually making new energy in its core. A white dwarf shines for a different reason. It is living on what it has left, and to understand how that stored heat came to be trapped inside such a small remnant, we have to go briefly backward to the final stages of the star that created it. For most of its life, a star like the Sun is remarkably stable. Hydrogen fuses into helium in the core. Gravity presses inward. Hot gas and radiation provide pressure outward. For billions of years, those two tendencies remain close enough to balance that the star changes only gradually. But the supply of hydrogen in the core is finite. As it becomes depleted, the core can no longer support itself in quite the same way. It contracts and heats. Hydrogen continues to fuse in a shell around the exhausted center, and the outer layers of the star respond by expanding. The star becomes a red giant. This phase looks dramatic from a distance, but the important change for our story is happening deep inside. As the central temperature rises, helium can begin to fuse. Through a sequence of nuclear reactions, helium is converted mainly into carbon and oxygen. Those two elements will eventually make up most of the interior of the white dwarf we are following. The star does not continue upward through the periodic table indefinitely. For a star in the Sun's general mass range, the core never becomes hot and compressed enough to sustain the later stages of fusion found in much more massive stars. Carbon and oxygen accumulate, but they do not become the fuel for another long, stable phase. Eventually, the usable nuclear fuel in the center is exhausted. Fusion ends. The outer layers are then lost into space through winds and episodes of mass loss. For a time, the exposed hot core can illuminate this expanding material, producing the glowing structure astronomers call a planetary nebula. The name is historical. It has nothing to do with planets. The nebula itself is temporary. Its gas expands. It becomes thinner. Over time, it blends into the interstellar medium, carrying material that was once inside the star back into the galaxy. At the center, however, something much more persistent remains. The compact carbon and oxygen core has been exposed. That is the white dwarf. At first, it is extremely hot. This is an important distinction. The white dwarf is no longer hot because fusion is continuing inside it. The nuclear reactions that powered the star for most of its life have ended. Instead, the remnant begins its new existence with heat left over from everything that came before. The long history of nuclear burning, gravitational contraction, and the formation of the dense stellar core. It is like a furnace. After the fuel has been removed, the fire is gone, but the structure is still hot. So when we see a young white dwarf shining brightly, we are not seeing a smaller version of an ordinary star. We are seeing a cooling remnant. No new reservoir of fusion energy is replacing what leaves its surface. Every photon that escapes carries away a small part of the heat it inherited at birth. That sounds as though the future should be simple. A hot object surrounded by colder space should radiate energy until it becomes cold. And at the broadest level, that is exactly what happens. But a white dwarf is not an ordinary hot object. Its dense interior conducts heat in unusual ways. Its thin outer layers regulate quickly that heat reaches the surface. Its composition changes as it cools. At sufficiently low temperatures, much of the interior can even become crystalline. So the next question is no longer how the white dwarf was formed. It is how an Earth-sized stellar remnant with no fusion left inside it manages to hold on to its heat for so extraordinarily long. Once the white dwarf has formed, its future becomes a problem of heat. There is no longer a nuclear engine replacing the energy that leaves. The remnant begins hot, then spends the rest of its evolution radiating that stored thermal energy into space, but the heat does not escape evenly from every part of the star. Most of the white dwarf's mass is packed into its dense interior, where carbon and oxygen nuclei are immersed in a sea of degenerate electrons. Those electrons move freely enough to conduct heat very efficiently. As a result, the deep interior tends toward an almost uniform temperature. That may sound surprising. The center of an ordinary star is much hotter than its surface. Inside a cooling white dwarf, the temperature still changes toward the outside, but across much of the degenerate core, the variation is relatively small. The real obstacle lies above it. Wrapped around the dense interior is a much thinner outer envelope, usually containing helium, and in many white dwarfs an even thinner layer of hydrogen. These layers contain very little of the star's total mass. Yet, they have enormous influence over how quickly the star cools. The reason is that energy leaving the core has to cross them before it can reach space. Deep inside, electrons can transport heat efficiently. Nearer the surface, the matter becomes less degenerate and the physics changes. Radiation and, in some temperature ranges, convection become important. The opacity of the material determines how easily energy can move outward. So a white dwarf does not cool according to its core alone. Its thin atmosphere and envelope act as a regulator between a large reservoir of internal heat and the cold universe outside. Mass matters. Core composition matters. The thickness and chemical composition of the outer layers matter. Astronomers have to model all of these things when they translate observed brightness into a cooling age. There is another simple rule working at the surface. A hot object radiates much more energy than a cooler one. For an ideal thermal radiator, the emitted energy per unit surface area depends on the fourth power of temperature, so a large fall in temperature produces an even larger fall in radiated power. A young white dwarf can therefore lose energy relatively quickly. Its surface may initially be tens of thousands of degrees, sometimes much hotter, soon after the remnant is exposed. It shines strongly in ultraviolet and visible wavelengths and moves through these early cooling stages comparatively fast. As the surface temperature falls, its luminosity also falls sharply. The remnant becomes harder to see. This basic behavior was placed on a mathematical foundation in the early 1950s by the astrophysicist Leon Mestel. His model was deliberately simplified, but it captured the essential idea: a degenerate interior containing thermal energy covered by an envelope that controls the outward flow, producing a predictable decline in luminosity with time. Modern white dwarf models are much more detailed. They include improved equations of state, realistic atmospheres, neutrino losses at high temperatures, convection in the outer layers, different core compositions, and physical changes that occur as the star becomes colder. But Mestel's work provided the framework for thinking of a white dwarf not merely as a dead star, but as an evolving thermal object. That distinction turned out to be extremely useful. If the cooling rate can be calculated, then brightness contains information about time. A hotter white dwarf is generally closer to the moment when it formed. A cooler one has generally been cooling longer. Not every white dwarf follows exactly the same track, but the relationship is structured enough that entire populations of these remnants can be used as clocks. Before we reach that, larger itself undergoes a change. Cooling does not simply make the same material colder forever. At a certain point, the carbon and oxygen nuclei that have been moving through the dense interior begin to organize themselves. The star starts to freeze. Not at its surface, and not in the familiar way that water freezes on Earth. Deep inside the white dwarf, matter enters a crystalline state, under pressures almost impossible to reproduce anywhere else. And that phase transition does something important to the very cooling process that caused it. As the temperature falls further, the carbon and oxygen nuclei inside the core move less vigorously. The electrons remain highly degenerate, continuing to provide the pressure that supports the star. But the nuclei themselves are governed by another competition. Thermal motion tries to keep them disordered, while their electric charges make them interact strongly with one another. Eventually, the balance changes. The nuclei begin settling into an ordered arrangement. The white dwarf starts to crystallize. This does not mean the star turns into an ordinary crystal like quartz, salt, or diamond. The pressures are vastly greater. The electrons are not bound into conventional atoms, and the forces holding the material together are unlike those inside a gemstone on Earth. But the word crystallization is physically appropriate. The ions move from a more disordered state into an ordered lattice, forming a solid phase deep inside the star. The process begins near the center, where the density is greatest, and gradually works outward as cooling continues. For many years, this was a prediction hidden almost completely inside math equations. Astronomers could observe the surfaces of white dwarfs. They could measure their brightness, color, motion, and atmospheric composition. But the core lies beneath layers of matter that no telescope can simply look through. There was no photograph that could show carbon and oxygen nuclei locking into place. The evidence had to appear indirectly, and crystallization creates exactly the kind of indirect signal astronomers can search for. When matter changes phase, energy is involved. Water releases latent heat when it freezes. Something conceptually similar happens inside a white dwarf. As the ions settle into their more ordered state, energy is released. There can also be changes in the internal distribution of carbon and oxygen. Because the two kinds of nuclei do not behave identically during crystallization, the resulting redistribution can release additional gravitational energy. The consequence is important for the cooling clock. For a time, some energy is being returned to the star's thermal reservoir. The white dwarf continues to cool overall, but its decline in luminosity can be delayed. If many white dwarfs of similar properties are observed together, that delay should leave a statistical fingerprint. They should spend slightly longer at the luminosities where crystallization becomes important. And if they spend longer there, more of them should be found there. In 2019, astronomers using data from the European Space Agency's Gaia mission reported precisely this kind of pattern. The distribution was not perfectly smooth. There was an accumulation of white dwarfs along part of the cooling sequence. More objects were lingering there than a simple cooling model without the relevant phase change would predict. The location of that pileup matched the region where models expected crystallization to affect the cooling rate. An event taking place inside stellar cores, completely hidden from direct view, had left a trace in the population of stars we could observe. This is one of the most useful moments in our journey. Until now, a black dwarf has belonged entirely to the future. We cannot find one. We cannot watch a white dwarf complete the journey. But we can test some of the physical steps along the way. Crystallization is one of those steps. It tells us that the cooling models are not merely stories projected into an unreachable future. At least part of that long thermal evolution is already unfolding inside real white dwarfs in the Milky Way, and its consequences can be measured. The deeper story has also continued to develop, so even here, the path is not a single smooth descent. A white dwarf does not simply grow dimmer at one unchanging rate. Its interior changes state. Energy can be released during those changes. Its composition can alter the pace, and later, at still lower temperatures, another regime becomes important, one in which the thermal behavior of the crystalline material changes again. That brings us to a correction that matters. The real physics is more interesting than that. Some stages delay the cooling. Others can make the remaining thermal energy easier to lose. The road toward a black dwarf is not one simple slowdown. It is a sequence of physical regimes, each governed by a different part of the star. Once crystallization begins, it becomes harder to describe a white dwarf with a single phrase, such as, "It cools more and more slowly." That picture is useful at first, but it is incomplete. The cooling history changes because the physical state of the star changes. Later, ordinary thermal radiation becomes more important. Still, later, after much of the core has become solid, the behavior changes again. A crystal does not store heat in quite the same way as a liquid. At sufficiently low temperatures, the vibrations of its ordered lattice carry less and less thermal energy. In solid-state physics, this low-temperature behavior is associated with the Debye model. The important consequence is almost the opposite of what a simple, ever slower story would suggest. As the heat capacity of the crystalline core falls, there is less thermal energy left for each further decrease in temperature. For some white dwarfs, especially more massive ones that crystallize earlier and more completely, this can lead to a stage in which the remaining heat reservoir is exhausted comparatively quickly. This is sometimes called Debye cooling. The star is still extraordinarily old by any human measure. Nothing about the process is fast in an everyday sense. But within the long history of a white dwarf, one regime can proceed faster than the one before it. That is why there is no single universal cooling clock that applies identically to every white dwarf. Mass changes the density of the interior. Composition changes when crystallization begins, and how much energy can be released during phase separation. The thickness of the hydrogen or helium envelope changes how efficiently heat escapes through the outer layers. Even interactions with the surrounding environment can matter in specialized cases. Astronomers handle this by calculating families of cooling models rather than one ideal track. Then they compare those predictions with real populations. This matters when we talk about black dwarfs. It is tempting to assign a single enormous number to the question. How long does it take? But there is no sharp moment shared by every white dwarf. There is not even one universally agreed temperature at which the word black must suddenly replace white. The term describes a far future state in which a white dwarf has become extraordinarily cold and faint, with very little thermal energy left to distinguish it from its environment. Reaching that state depends on which white dwarf we are following, and on what we mean by effectively dark. The environment itself will not remain fixed either. The cosmic microwave background is about 2.7 Kelvin today. As the universe expands, that background radiation continues to cool. The target is not simply today's cosmic temperature waiting motionless at the end of the calculation. This is why very large future timescales should be treated as model-dependent estimates, not as dates written permanently into the laws of nature. What remains much firmer is the scale of the mismatch. The universe is about 13.8 billion years old. Real white dwarfs have cooled for billions of years, and even the oldest examples we observe are still warm enough to radiate measurable energy, whatever precise threshold we choose for a true black dwarf. The present universe has not provided remotely enough time to reach it, and we do not have to rely only on calculations to see that. The cooling process has left another signature in the sky. By counting white dwarfs according to how bright they are, astronomers can see where the oldest members of a stellar population simply run out. That faint edge turns cooling into a clock, and it gives us a way to measure cosmic age using the remnants themselves. The faintest white dwarfs are difficult to find one by one, but taken together, they become easier to understand. Instead of asking how old a single white dwarf might be, astronomers can examine an entire population and count how many remnants appear at each level of brightness. This produces what is called a white dwarf luminosity function. The idea is simple. Young white dwarfs are relatively bright because they still contain a large reservoir of thermal energy. Older white dwarfs are dimmer. If cooling proceeds in a predictable way, then the distribution of brightnesses across a population carries information about how long that population has existed. At the bright end, white dwarfs move through their early cooling stages comparatively quickly. At lower luminosities, they spend more time, so more objects tend to accumulate at the faint end, but the sequence does not continue forever. Eventually, astronomers reach a brightness below which the population suddenly becomes sparse. There is a cutoff. The reason is not that white dwarfs stop cooling at that point. It is that the population has not existed long enough for any of them to become much fainter. The cutoff is therefore a clock. In the disk of the Milky Way, the faintest white dwarfs reveal how long stars have been forming and dying in that part of the galaxy. In older populations, such as globular clusters and the galactic halo, the cooling sequence extends farther, because those stars began their lives earlier, and it carries an especially useful feature for our story. The absence of colder white dwarfs is itself information. If the universe were vastly older than our other measurements suggest, then some white dwarfs should have had enough time to cool much farther down their tracks. We do not see that. Instead, the faintest remnants appear where models of stellar evolution and cosmic age say they should. The edge in the distribution agrees with a universe that is old by human standards, but still young compared with the thermal lifetime of a white dwarf. This is a quieter kind of evidence than a dramatic image from a telescope. There is no single photograph of cosmic youth. There is a population, a count, a boundary in brightness where the oldest remnants simply run out. That does not make the method useless. It makes the agreement more interesting. The same physics that explains the interiors of individual white dwarfs also helps reconstruct the history of entire stellar populations. A dim remnant can tell us something about the star that created it. Thousands of dim remnants can tell us something about the age of the galaxy. And the faintest edge of all tells us something about time itself. So we have now reached an important point in the journey. The idea of a black dwarf began as an extrapolation into a future too distant to observe. But the path leading toward that future has left several measurable traces in the present. We see white dwarfs cooling. We see evidence of crystallization. We see populations whose faint limits match the ages expected from other parts of astronomy. The clock is running. It has simply not been running for very long. From here, we can finally allow the scale to widen. We can leave the present population of the Milky Way behind and ask what happens after ordinary star formation has faded, after the longest-lived stars have spent their fuel, and white dwarfs become some of the most persistent objects left in the cosmos. Only then does the idea of the black dwarf move from distant prediction toward the natural landscape of the far future. To reach that landscape, we begin with what is still abundant now, stars. New ones continue to form inside cold clouds of gas. Others are nearing the ends of their lives. White dwarfs are being created now, and many more will appear in the future. But ordinary star formation cannot continue forever at its present pace. The raw material is finite. In standard long-term models, the era of ordinary star formation eventually fades. The exact schedule depends on assumptions about how galaxies evolve, how gas is recycled, and how often new stars can still form through rare interactions. But on timescales around 100 trillion years, the bright stellar universe we know is expected to look very different. The longest-lived stars will still matter most. Small red dwarfs use their hydrogen very efficiently. They can survive for trillions of years, far longer than the Sun. Eventually, even they will exhaust their fuel. Then the balance of the cosmos shifts. White dwarfs, neutron stars, black holes, planets, and other remnants become increasingly dominant. For our story, the important survivors are the white dwarfs. They continue doing exactly what they are doing now. They cool, their surfaces become fainter, their internal crystals grow. The remaining thermal reservoir diminishes, and the background universe around them also changes. Today, space is filled with the cosmic microwave background at about 27 Kelvin. That radiation expansion becomes colder, and its characteristic wavelengths stretch. So the future white dwarf is not cooling toward a fixed room temperature. Its surroundings are changing too. This is one reason there is no single precise date when we can say the first black dwarf must appear. The phrase black dwarf describes a practical end state rather than a sharply defined phase transition. It means a white dwarf that has cooled so far and become so faint that very little thermal energy remains available to distinguish it from its environment. Exactly when that description becomes appropriate depends on the mass of the remnant, its internal composition, its outer layers, and the physical threshold we choose. But none of those details changes the central answer. The universe today is nowhere near old enough. We can see the beginning of the process. We can observe white dwarfs that have cooled for billions of years. We can detect the effects of crystallization. We can use their luminosities to reconstruct the ages of stellar populations. But the black dwarf regime belongs to a future separated from the present by an enormous gulf in time. That is the answer hidden inside the title of this journey. The universe has never made a black dwarf because the cooling clock has barely begun to run. Not because white dwarfs are failing to cool. Not because the underlying physics requires an unknown force. And not because black dwarfs are hiding beyond the sensitivity of our telescopes. The necessary time simply has not passed. There is a useful restraint in that conclusion. We do not need to pretend we know every detail of the remote future. But the early part of the path is already visible. A real white dwarf can be measured today. Its temperature can be estimated. Its cooling behavior can be modeled. its crystallization can leave a mark in population data. It is the far end of a process whose first steps are happening in the sky now. And that leaves one final question. If we continue following the remnant beyond the part of the story we can test directly, what can physics still say with confidence, and where does confidence finally give way to conditional possibilities? Beyond this point, the story becomes less certain. The cooling of white dwarfs is well grounded in physics we can test today. Their structure is understood through quantum mechanics. Their temperatures can be measured. Their crystallization can be inferred from real populations. Their cooling sequences can be compared with the ages of stars and clusters. But the farther we travel into the future, the more assumptions begin to matter. One of them concerns the stability of matter itself. Some theories of particle physics allow protons to decay over immense timescales. No such decay has ever been observed. If protons eventually decay, then the matter making up the remnant would not remain unchanged forever. Over sufficiently long periods, even a cold stellar corpse could gradually lose its structure through processes that are still hypothetical today. If protons are stable, the story is different. The remnant could survive vastly longer. Under that assumption, theoretical work has even explored whether certain massive black dwarfs might eventually undergo transformations driven by extraordinarily slow nuclear processes on timescales so large that ordinary astronomical language becomes almost useless. These are interesting possibilities, but they are not observations, and they are not required to answer the question that brought us here. We only need to return to the white dwarf where our journey began. It is small. It is dense. Its nuclear reactions are over, and yet it still shines. That faint light is the important part. It tells us that the remnant still carries heat from an earlier stellar life. It tells us that the cooling process is incomplete. The older remnants are fainter. Some have begun to crystallize. The cooling sequence extends downward. Then it stops. Not because physics has reached an endpoint, but because cosmic history has not yet lasted long enough to populate the colder part of the curve. So the black dwarf remains where it has always been in our story. Not hidden, not missing, not waiting somewhere beyond the reach of a better telescope, simply not made yet. The universe has had enough time to form galaxies, stars, planets, and white dwarfs. But it has not had enough time to carry that process to its far end. And perhaps that is the quietest meaning of the black dwarf. It is not a monument to darkness. It is a measure of time. For now, the oldest white dwarfs remain visible. Their light is weak, but it is still there. And inside that fading light is a future that has not happened yet.